So, okay, while they're setting this up, welcome to the surprise talk by say short talk. So, and very, very informal, but also tends to lead to very heated discussions. So maybe we will let Gil give a 10-minute presentation and then ask questions. How about that? Yeah? Good.
So this is not supposed to be a talk. I thought about it as a conversation, and it's what? No, you can talk back. In fact, well, let's have it as a discussion. So I don't know why. Maybe we can. Okay. So I want to spend some of the voice I have to congratulate you for this wonderful school. And this is a really, quantum computation is a wonderful topic which relates to many things, to many areas of physics and to mathematics and computer science. And so this is a sort of here I've talked about quantum supremacy and mainly about Google quantum supremacy demonstration. Here is hi boss. Here is you see the first strings in the quantum supremacy experiment, the first experiment, the flagship quantum supremacy experiment. So this is something that represents a superior power of some sort. You may use it for prayers or some other things. And okay, so beside being I don't know what happened, but besides being against critical of the Google experiment, which is only a recent thing, I'm also critical about quantum computers in general. And so I think everybody is going to fail. The good guys, the bad guys, the nice guys, the honest guys, the dishonest guys, everybody. And there is a short argument which is on this slide. Why my argument against quantum computer? But I will not talk about it because this is a more extensive talk. This is less, I would say. I can't say that everybody except, okay, let's say few people agree with me, and few people understand this argument, and even fewer people agree with this argument. But I think it's pretty good argument. I don't think it's a ironclad argument, so I don't think this is the reason for all these efforts to stop. And but now we will, and if you want to read more about it, there are various posts that I wrote about it. And I want to talk about the Google experiment, and I want to share with you the initial thought about the Google experiment. Let's discuss it because you know this. So the first thing that caught my eyes is that the paper describe a speed up of 300 trillion times. So something that takes a quantum computer 600 seconds take a core 50 trillion core hours. And even the authors were very pedantic to mention that not only that it is 600 seconds, but actually the quantum computer rested most of the time and only worked for 30 seconds. So it's even 6,000 trillions. So, of course, I don't think part of my argument is that quantum supremacy, you know, we need to define it, so on, but that huge or large advantage over classical computing is not possible certainly by NISQ systems, noisy intermediate scale quantum systems. But my reaction is that even if you believe that quantum supremacy is possible, it looked to me like it's too good for the first experiment. It's like the President of the United States announcing in the first landing on the moon that actually the astronaut landed on Jupiter. We can talk about it. You think, what do you think? It makes the results stronger or weaker? Yes.
Isn't this intrinsic to exponential advantage? Like if I double my RSA key size, then I also, isn't decrypting that also 300 trillion times slower?
Yes, I agree that if you can get exponential advantage, then you will get very large numbers, but maybe not in the beginning because there are some other parameters that it's hard. And also, it's better to have a smaller advantage that you can prove than a larger advantage that the proof is a little bit shaky. Well, as we know, this 300 trillion can be reduced. So, but you know, this is something you can think about it. But this is not a serious attack about this. And what I have to say about the Google supremacy demonstration, it represents a very large leap in several aspects of human ability to control quantum systems. It should be checked carefully, and of course, it should be successfully replicated, as we expect from what we want to get to enter the scientific fact. And the support for the experiment in the classically trackable regime is too weak to be convincing. So, you know, there are some regimes where we can check things by classical computers, and there are too few experiments and they are not sufficiently convincing. And some findings of the paper are too good to be true, and this is something I want to elaborate. I'll talk only about that. And my current assessment is that both the Google supremacy claims and their other central claim about fidelity estimations are incorrect. So, you know, this is what I think. And here is the centerfold of my, and this is this amazing claim. So actually, the Google experiment have two major scientific discoveries. One is the quantum supremacy, the fact that the quantum computer can do computation that classical computer needs, thousands of years. And the other is that they can estimate the fidelity of a quantum computer using a very, very simple high school probability formula. Of course, this formula is a good estimation, but what is amazing is that in about 300 experiments or 250 experiments, this formula gives you a prediction up to 10 to 20% of the true fidelity of the computer as computed by a certain statistical test. And if you want even slightly simpler formula that will cost you maybe 5 additional %, is this formula. You have a quantum computer, and this is a system with about 1,000 quantum gates and 50 qubits. You take this number 1 minus 0.038 to the number of qubits, 1 minus 0.0016 to the number of gates, and this number to number of 2 qubit gates. And this product gives you precise estimation on the fidelity. And so the question is this an amazing breakthrough in quantum engineering, in engineering as a whole, because we don't witness anything similar like this, as far as I know, in any other areas of engineering.
Can't you think of this as just the first order approximation?
Yes, you can think about it as a first order approximation, but you would expect that various effects will cause the value of this approximation to be in the thousands of % and not 10 to 20%. And actually, you don't need it for quantum computers. You need it. And okay, so I'm quite amazed by that, but you can see that it's not only me, and this is what John Martini had to say about this. Maybe somebody is willing to read it because I'm losing the voice. Oh, please.
Sure.
Oh, go ahead.
Where's the microphone?
Yeah, another microphone.
Too good.
Yeah, you don't have to read the title. Too good to be true is something I said, not John Martini. Yes.
John Martinez, now I want to point out what is the most amazing thing about this data and why. If you want to think about it in a funny way, why we, quantum scientists, can all keep our jobs or maybe get more funding, even better. And this is the idea. Look at this. Oh, sorry. And look at, and this is the data. Look at this black line here. It is just a simple prediction from the 1 and 2 qubit simulations data that I showed you before. You multiply all these fidelities together in a totally classical way. This is a high school probability theory, and it predicts what is going on in this very, very, very complicated system with all this quantum computation going on. That, to me, is absolutely amazing that such a simple model for errors works so well. That was the big surprise. When that happened, when we got the data, it was the big surprise here. And of course, if things were worse, I wouldn't be standing here talking to you today.
Okay, so let me summarize what is my view about this formula. So I regard the claimed success of this formula, Formula 77, as an unbelievable nonsense. So it's not just a nonsense that it's hard to believe that it's true, but it's unbelievable that scientists will seriously claim such a thing. The Google team, on the other hand, I should say everything I say before I write it or talk about it, I correspond with the Google people. The Google team doesn't think it's unbelievable nonsense, and they have some statistical justification for this amazing success. And we will need to find the right scientific context and methodology to study it. Reliability theory seems to be relevant. And I should say that the amazing prediction power of Formula 77 is not required for quantum computers. So for quantum computers, all you need is a guarantee that the fidelity is low. But you don't need this magic formula to compute it correctly. It's only needed because of the indirect, complicated extrapolation logic of the Google supremacy argument. So it's not really needed for quantum computing. What to do now? Oh, okay. So here is another demonstration of this formula. You see here two scientific experiments of two circuits with different number of qubits. One is called the full circuit, the other is called the patch circuit. They're not identical, the numbers are slightly different, and this is the fidelities. And it's quite amazing to see such an agreement, even if you run the same experiment twice. And here, this is really an unheard of agreement between two complicated physical experiments. It's so good that Nature magazine could save some of the blue ink because the orange was just on top of it.
Gil, sorry, in 2 minutes we're going to go to Q&A. So if you
What?
in about 2 minutes we're going to
Two
let
minutes,
people
okay.
tell you why you're wrong. So
Okay, good. Actually, I have just 2 more slides. Here's another example. You see here 3 pictures. We have 3 figures of 3 analytic maps and 3 samples drawn according to this analytic distribution. In 2 of the cases, the samples were drawn perfectly by a computer, and in 1 of the cases, they represent a very complicated physical experiment. Now, test your intuition, which is which? Can you see the difference? Well, I cannot see the difference. The truth is that the orange is the sample from the quantum computer, or the other were done, but maybe there's no difference. And here is the end. What is needed to be done? Verification and analysis of the data set, larger samples and further experiment in the classically tractable regime, blind test. I think the crucial thing, as in most of science, is that the Google guys will have blind tests so that they don't know in advance the circuit that they are trying to work on. And I think there should be careful examination of the experimental data and the supremacy claims, both by the Google Quantum Computing Group itself, by the scientific community, and by Google. So here I thank you. I just want to mention, if you want, what happened? Okay, I just want to mention that Peter Shor in a tweet pioneered another area, how to respond to quantum computer skeptics by poetry. And there was and you're all invited. I think if something will convince me, it is poetry, that I'm wrong. So if you have poems, you're invited to contribute. And the best poem in my mind is this poem by Renan Gross. So again, I don't want to lose somebody is volunteering to yeah. Yeah.
Okay.
This
So
requires
this is
some.
funny because I'm now reading the skeptic one. But okay. Bit by bit, as if on cue, the beat of qubits slowly grew to fit the never-ending queue of them who bit more than they could chew. Yet there is hope. For quantum queries clear with wonder, quibbling quarrels break asunder, quenching squabbles, quitting squander. Quite quaint quest for us to ponder. Shall we not try?
Okay. Okay, Q&A, yeah.
All right. Any questions or comments or,
Yes.
controversial?
In the same way that Google did an experiment in order to prove quantum supremacy, do you have an idea to make an experiment in order to disprove it in an experimental way?
Yes, I think, for example, okay, so that's a very good question because there are a lot of aspects of quantum supremacy. Some people claim that also in nature there are some phenomena that require supremacy. I think probably this is also incorrect. And I think a good step will be to shoot down the Google experiment. So, of course, we need to shoot all the experiments, but Google is a major player, and if this will be some support. But I think to believe in some supreme power is always very hard to disprove. But there are various directions. For example, there are theoretical consequences of the inability to achieve quantum supremacy and quantum error correction. This is more important, which are fairly interesting. Yes.
Let's let Adam you can go first.
Yeah, so the main objection you seem to have is that the Google data looks too good or something in some sense.
Yeah.
So my question is, do you think the Google data is incorrect in some way? And if not, then if
what
so,
is the
that's one thing, and then if
explanation?
not, yeah.
That's also a very good question. And I think this is typical to many scientific things, that sometimes you found some irregularity in the data, and usually it's very difficult to find the precise explanation, the precise methodological mistake that can cause this. And this is, of course, a delicate issue on its own, and there is more to study. This is not the only thing, this Formula 77. There are other aspects. So the answer is I don't know. But I think if you find irregularities in the data of this kind, this is not a good sign.
But I have a question. If you assume everyone in Google is honest,
Yes.
is
This is the same question, no?
I just wanted no.
It's just more.
Data being incorrect is a different thing. But I'm really asking, would the argument not hold if you assume, like, if I mean, scientists can make mistakes
okay,
even
this
if
is
they're
also
honest.
an excellent question. In general, we want that the scientific proofs will not depend on believing things that we can check. So the question, if I believe they're honest or if I don't believe they're honest, it's not
But
relevant.
I think really what this kind of curve showed is that their data appears to be consistent with a really simple IID error model.
Yeah.
So I agree that it doesn't necessarily prove that model's there,
No,
but
not-
in some sense, what more could you have asked from the experiment
not-
other than showing it's consistent?
No,
like
wait,
it's an experimental
it's
result.
not only with the IID, it also said that there's no systematic bias on the individual terms, which is also can happen, and it's also unreasonable. So it's assume a lot of things which are unreasonable, including this full IID, and it's unreasonable. What can I ask if you get unreasonable results?
There were 10 or
then
20% deviations, so it's just saying this
Yeah,
is the
but-
first order approximation.
No,
that
no,
looks
10 or
like
20%
IID.
when you have 1,000 multiplication of 1,000 numbers and you get 10 of 20%, this means that there is no systematic bias. So all the averages are precisely correct. Because, so this is, this is precisely the question that should be asked in the context of reliability theory, which study precisely this question. So reliability theory, there are many examples of systems of this kind, and we can see what happened in other cases.
Just a
So-
second, so you'll ask the last question, and then we're gonna go to Adam, who will sort of tell us a bit more so that we can ask harder questions in the panel.
So I guess the question, this question about this Formula 77, which just because I don't know this as well, is it the case that basically they have underlying gates that fail with very low probability, and that so overall when you take a product, you take a product of things that are very close to 1, like 1 minus epsilon, it kind of behaves, you take a product of k times, it kind of behaves like 1 minus k times epsilon, and,
Well, not
and
precisely,
plus some
because-
correction terms, etc., because you kind of go...
No. It's in the range where it doesn't. If you compute 1 minus k times epsilon, will be well below 0. So
Well, or just a little?
well below 0. The outcome will be about 1 over 1,000 of all these very high numbers. So this is not. You have actually to multiply them.
Yes.
And yeah. So what's your question?
No, I get, because I guess what I wanted to say is that at least say if you were in the range where 1 minus epsilon to the k is roughly 1 minus k epsilon, many different noise models could give you the same kind of results.
You're not in the range. Don't worry. But the problem is if you change epsilon a little, then this is already much more than this 10 and 20%. So this means that they also know the value of epsilon, the 0.0063 is extremely accurate.
Well, I guess if they tested each gate, 1,000 times, then they should know it up to accuracy 1 over square root of 1,000 or whatever.
This is also not correct, but never mind. Yeah.
Okay. Let's thank Gil.
We're going to hear more about this in the panel, I assume. Let's not put Gil and Boaz too close to each other.